Hello everyone. In this video, I'm going to discuss Horspool's algorithm. Horspool's algorithm is a string matching algorithm which uses what we call input enhancement. Before getting into that, let's see what is a string matching problem. String matching problem is to find the pattern of length m in a text of length n. Finding a pattern of length m means a substring of length m within the text should match with the pattern of length m, right? So let's see a brute force way of solving this one. So in this one, we try to match with every possible substrings of length m in the text with the pattern, right? So the first substring starts at 0 and it runs up to t of tm or tm minus 1 because it's of length m. And then second substring starts at t1 and then runs up to tm. Third one starts at t2 and then runs up to tm plus 1. Likewise, the last one will start at tn minus m and runs up to tn minus 1. So there are n minus m plus 1 substring to be precise, right? So we try to match with all of them one by one, and then if any one of them matches, we say a pattern, the pattern is found in the text. Otherwise, we say it's not found. So here is the algorithm. Obviously, it takes a text of length n and a pattern of length m as parameters, and index I is going to point to the first character of the substring of length m. So as I said, the first substring starts at 0, second one at 1, likewise. The last one starts at n minus m. So in total, there are n minus m plus 1 substrings. And within a substring, j is going to point to the first character in the pattern, right? So j will also tell you how many characters are successfully matched so far. So here is the matching we do in the while loop. Uh, the character in the pattern we are going to match with the character in the text starting at I, and if all of them matches one by one, if one of them matches, we increment j here. So if all the characters match, so j will become m, and when j becomes m, this condition fails, so it comes out of the while loop. And when j equals to m, obviously we found the pattern in the text, so we are going to return I, which is the index of first character of the substring, which is same as the pattern, right? So that's a successful case. In a failure cases, in a failure case, uh, a character of the pattern doesn't match with the character of a text. In that case, this condition is false, and then it comes out of the while loop, and j will be less than m in that case, and obviously this condition is also false. So it looks for the next I, so it keeps on doing it. So if you don't find any of the successful cases, then we come out of the for loop eventually and say it's not found. So success case is returned here and failure case is returned here, right? So now the time efficiency of this one would be, in the worst case, it is order of nm. um, but for a natural language text, uh, such worst cases are rare there. That's why the average case for a natural language text is very close to n, which is order of n, which is a pretty good case already, right? But we have better algorithms where they improve that average case efficiency even more. uh, so all these algorithms are based on one of the criteria, where in brute force, what we try to do is, every time one of the substring matching is failed here, we increment I by 1, which is, that means we look for the immediate next substring in that. But in these algorithms, we use some of the other conditions and then try to shift that pattern by more than one. So in the brute force, we always shift the pattern by exactly one character. Here we try to shift by one or more characters at once, so that way we improve the string matching. So here are the well-known three algorithms. Horspool's algorithm is a little simplified version of Boyer-Moore algorithm, and Boyer-Moore algorithm and Knuth-Morris-Pratt algorithm both are pretty much same. So in this video, I'm going to just discuss about Horspool's algorithm. So, okay, here is the text of length n, and here is a pattern of length m. In all these input enhancement algorithms, we take the pattern and then we do some enhancement on that one, and then that's how we improve. If you don't know anything more than the input string, obviously we'll have to fall back to this a brute force approach. So here we do that input enhancement. So this is how we are going to create that input enhancement table. So we have a text here of length n, and then this is the pattern. And in this Horspool's algorithm, we start with matching the last character in the pattern with the last character in the substring, and we keep going from right to left. If all of them matches, obviously that's a successful case. If there is a mismatch at some point, what we are going to do? So if the mismatch happens in the beginning itself, and in this case, if this character, in this case it is s is not present anywhere here. In brute force, we would have shifted this pattern by one character, and then e would have come here below s, right? Now we know that s is not going to match with e before add, and it's not going to match with any of these characters in this case. So why shift by one or two or three characters in this one? Let's shift by six characters, so that none of these five characters are going to be below this s, right? That's why length of this pattern is 6, and then we are going to shift by 6 characters. That is safer because s is not going to match with any of these, right? That's something we already know. Now suppose again a similar mismatch happened, but this particular character, whatever is mismatched, is present in the pattern. In this case, I don't want to take a risk by shifting all characters by 6 characters, because what if this b is matching with this b, and then there is b a r, and then this b and e r, so the barber text is here, substring is here. So we don't want to miss that. So that's why I want to shift as long as a b appears below here, the first b appears below this b, right? So that is just a two characters away here. So in this case, I would like to shift by two characters, because shifting by one characters is going to be a failure for sure. We know that. So I'm going to shift by two characters, right? So that's why b is now below this b. All right. So now let's see two more cases. So these are the first two cases we saw, and suppose some of first few characters match properly, and then now there is a mismatch here. Now even then, let's not worry about which character mismatched here. Let's look at again the first character itself. Let's try to shift it. R is matching here for sure, but if we shift by one, this R is already gone. So among these five characters, none of them are matching with R, right? So then we can safely shift by six characters again. So all we need to look here is this last character. Is it present anywhere in these first m minus 1 characters? If it is not there, shift by the length of the pattern. In this case, again there's a mismatch here, and look for r is present here, so we want to shift until this r comes under this r, right, which is only three characters. That's why we are going to shift this pattern by three characters. So this r is here below this r, right? So these are the things we are going to use at any time. If there is a mismatch in between, we look for the last character in the substring of the text, and look for that in the pattern in the first m minus 1 characters. The rightmost we are going to match with that, right? If it is not present, obviously we'll push everything, we'll shift the pattern by length of the text. So we are not going to do that. So here, whenever we see this character, if there's a mismatch, instead of looking at wherever it is present, it is present at two characters away here, and in this case it is not present at all. So these things we should not do it at runtime. We should be able to do that in constant time. So that's why we are going to create a table called shift table, so that whenever we see a character here, we just look up for that character and look for a number, and that number should tell me how many characters I should shift the pattern to the right side. Right. So that is what we are calling it as T of C. C is the character. If this is the character in the last here in the text, and how many characters I can move the pattern on the to the right side. If C is not among the first m minus 1 characters in the pattern, obviously the pattern's length m is my shift value for this character. Otherwise, uh, look for the distance from the last character till the rightmost C in the first m minus 1 character. So the rightmost C is, in this case, this is the rightmost character with which is matching here. In this case, R is not anywhere present, so that's the first case. This R is present here, so this is the rightmost case. Even though it is present here, this is the rightmost case. So 3 is going to be my value for shift value for this case. So we calculate that one beforehand. That is what we call it as input enhancement. So we create that table, shift table, and then use it in the algorithm. So creating a shift table is pretty easy. While creating the shift table, not just the characters in the pattern, we should look for all possible characters in the input. So which we typically call it as alphabet. So for the whole alphabet, try to create a table, a shift table, and so here is so input for this shift table is obviously the pattern, and the output of this algorithm is a table. That's a shift table, and the table shift table is of length size. Size is the size of the alphabet. How many characters we are going to have in total? How many unique characters we are going to have in the input text and also pattern? Right. So to start with, initialize all the characters in the alphabet with m, which is the maximum possible shift, and then run through the pattern from the beginning to end, and then update the shift value, which would be better than m, which would be lesser than m. Right. If it is present in multiple times, what do we do? So initially, so suppose, how do we create a shift table for this particular string? It is of length m. So for the whole alphabet, initialize it as 7 to start with, and then start processing from here. R would be the value of shift value for R would be 7 minus 1, because in this form 7 minus 1 minus 0 is 7 minus 1, which is 6. So we'll start with 6 as the value, shift value for R, even though eventually it will be 3 here because 3 is present here. So it's going to be 6 for R, 5 for E, then 4 for O, and then R is re-updated as 3, and D would be 2, and then E would be updated from 5 to 1 year. So that's how we are going to create the whole shift table, right? Now let's see that with an example. Suppose we have a text here. So while creating the shift table, I don't need to know the real text. All we need is the pattern, and then we need to know the alphabet. Alphabet is what kind of characters I would be getting in the whole text. So suppose in this case my alphabet is all the 26 letters of English and a space. So these are the 27 characters in my alphabet. So shift value for each of those characters would be, to start with, as we said, we are going to initialize with m. M in this case is 6. So we'll initialize with all of them as 6 to start with. So all of them would be 6 initially. And then I start processing the pattern here. So B value would be updated as 6 minus 1, 5. So it would be 5 to start with. It was 6, it became 5. It will become 2 eventually. So A would be 4, R would be 3, and then B is updated again with 2, and E would be updated as 1, and we stop there. We don't look for the last character. That's because last character anyway we are going to shift by at least one character, so the last one will anyway move outside of this one, right? So all we try to do is we try to align this character with one of the characters in the pattern. So let's run through an example and then look into the detailed algorithm. So suppose, okay, this is the pattern and this is the shift table we got, and and this is the text we have, so we start with aligning the pattern of length m with the first m characters of the text, which I am calling as the first substring. So in the algorithm, I start matching with the last character of the substring with the last character of the pattern. If it's a mismatch here, so I'm going to look for the shift value for A here in the table, which is 4. So I move the pattern by 4 characters. I shift the character by 4 characters. Now, all we are trying to do here is basically we are trying to align this A with the A here, right? So that there is a possibility of barber here. Maybe it's not here, but there is a possibility, right? Now again start matching with the last character. E and R didn't match, so look for E in the table, it says 1, so shift the whole pattern by one character. So the E came, this E came here, and it is matching with the E in the text. Now R is matched with space here, and obviously it's a mismatch, and look for the space in the table, it says 6, so shift the pattern by 6 characters. So next pattern is here. Now R is not matching with B again, and B, look for B, it says 2, so shift the pattern by 2 characters. So the B is here. Now it's matching with this. Now it matched with R here, that's a good match. And then we go to the left, A is not matching with E, so look for A, it says no, look for R actually, because the last character is the one we got to look. It says 3, so shift the pattern by 3 character. Now all of them match. R is matched here, E, B, R, A, B, all of them matched. So this is a case of successful case, and we need to return the index of this character. That's how the algorithm should end. So in total, the algorithm should work this way. Given the pattern and the alphabet, we can create the shift table, and once the shift table is ready, align the pattern with the first m characters of the text, which is the first substring, and start matching with the last character of the substring with the last character of the pattern, and move from right to the left. And if all of them matches at any point of time, like it happened here, then return index of the first character of the substring as a successful case. Otherwise, if there is a mismatch, look for the last character of the substring in the table, and whatever value it says, the shift value, shift the pattern by so many characters. That means basically my last character index would be moved by so that number here, and then we keep doing it until either we get a successful case like this, or the pattern moves beyond the text, right? And in that case, uh, that means the pattern is not present in the text, right? Let's see the algorithm which is doing exactly what I just explained. So we have a pattern of length m and a text of length n as input, and so initially we create the shift table as I explained earlier, so which takes input as the pattern, and also it should know the alphabet. Maybe you can treat that as an input or something like an implicit thing. Now we are aligning the pattern with the first m character or the first substring. So we are going to start with the last index here. So I'm going to initialize I with here. In this case, the length of the pattern is 6. That's why the index of I would be I value of I would be 5, which is the last character in the substring. So I is initialized as m minus 1. And then this loops runs for and runs until I is less than or equal to n. So we can keep on going until I is starting here. So I could be at n minus 1 also. That is still a valid case we should consider. When I crosses n minus 1, that means we are already going beyond the input text. So in that case, we'll have to say that the pattern is not found. So as long as I is less than or equal to n minus 1, we keep doing it. So K indicates the number of successful characters matched in the substring for the pattern. So this while loop tries to check for each of those matches. So this is the character in the pattern, and this is the character in the text we are matching there. If any one of them mismatches, then it's a false case and then comes out of the while loop. In that case, K would be less than M, because K indicates the number of characters matched. So this would be false, and then it has to increment I, and it increments I by table of Ti. What is Ti? I is basically pointing to the last character in the substring, right? So we look up for this value in the table, and whatever the value it says, we increment I by that. So A is 4 here, and it was pointing here at 5, and then I would be incremented to 9. So it will come here because that is the last character we are going to match here. So that's why I is equal to I plus table of shift value for ith character. So this is a false case whenever an unsuccessful case, and then we keep looking for that. If I is still less than or equal to n, we keep looking that for that, and at some point, if all the m characters match, and every time we are incrementing k here, so then k becomes m, k will be equal to m. In that case, this condition fails, so we come out of the while loop, So k equals to m is that case, and that's a successful case. So we need to return, suppose in this case it happened here, right? So suppose if it happens here or wherever, suppose if it happens here at 9, right? So but 9 is not the first character which matched of the substring which matches the pattern. The first character is somewhere here, right, which is exactly m minus 1 characters earlier, because I is pointing to the last character of the substring. I minus of m minus 1 would be the first character of the substring, right? So I minus of m minus 1 is same as I minus m plus 1, right? So that is the first character of the substring. So we are going to return that value, right? So yeah, now the worst case of this algorithm also in the order of nm, and the average case is obviously very nearer to linear, which is order of n. For natural language text, obviously it is much nearer to order of n. Even for otherwise, it is still very nearer to order of n, right? So applications of this algorithm is huge, because it's a very generic string matching algorithm. Whenever you say control F in any text, probably this could be the algorithm used. Uh, but yeah, here is a typical example of typically we have a DNA sequences of a huge length, like a billions or trillions or of more of length, and the whole text belongs to an alphabet called A, C, G, T. So these are the only four possible symbols in the sequence, and typically we are interested in finding a gene segment in that. Gene segment is a pattern we want to find in the DNA sequence. So in this example, we have a gene segment of length 10 and then a pattern of little longer length. And then how do we find this pattern inside this text? So obviously, along with the, if I go with the Horspool's algorithm, I would create a shift table with this pattern and the alphabet, and uh, and then start matching with the first substring, and then run the Horspool's algorithm from the last character of the substring. Whenever there is a mismatch, I look for the table for the character here, and then whatever the number it says, we are going to shift it by so many characters to the right. And we keep doing it until we find a successful case or the pattern goes beyond the text, right? In this one, finding the shift table is actually very easier. If I look at here, it's a the value of t would be 1, value of c would be 2, and then value of a would be 5, and then value of g would be 10, because g is not present anywhere here, right? Right. Yeah. So in some other video, I'm going to cover Boyer-Moore algorithm. Thank you for watching.